So when we start working with indices, there are two types of indices that we often come across that we sort of refer to a lot, and it's good to get to know these types of numbers, and we refer to these as square and cube numbers. Now, being able to identify squares in particular, but also cubes really quickly is a handy skill to have, but being able to know what they actually represent first is the first step of that skill. So essentially, a square number. We sometimes refer to these as perfect squares, but essentially what they are is they're a number that can be represented as the whole number of side lengths of squares. Like, let's kind of illustrate this, because that's going to be the best way moving forward to try and demonstrate what I mean. So let's just take a square. Pretend this is a perfect drawing of a square. All right. If I had side lengths 2 and 2 on this with my square, all right, I can break these into essentially 2 rows of 2 units of length. All right, and I can add all the squares up in between, and it gives me the area inside, all right, but it also tells me what the value of this is, which is going to be 4, okay? But we refer to this as a 2 by 2 square, which we know can be represented as 2 squared, 2 times itself twice, and the result of that is equal to 4. Now, we can extend this with any type of size square. So let's say that I've got a square that's 3 by 3. All right, so it's 3 lengths across, 3 lengths down. Essentially, we can break this up into the 3 by 3 here. And what you'll notice here is we've got 9 when we multiply these two together. All right, it breaks it down into 9 different little squares, but we can represent this sort of situation as a 3 by 3 square, which when we multiply them together will equal 9, or 3 squared, I should write it down. So it's in index form. All right, so often what we refer to this, rather than 2 to the power of 2, 3 to the power of 2, we call this 2 squared, 3 squared, and we say that 4 is a perfect square. All right, 9 is a perfect square. So you can keep extending this. So let's just quickly have the 4 by 4 so we can look at this. But essentially you can apply this for any value of whole numbers, essentially. What am I doing for? So, doing it the best I can, but we've now got a 4 by 4, and if we added them all up, we'll get a result of 16, okay, which we could have just done 4 times 4 to get that, which is 4 squared. So 16 is a perfect square. Now, this does also apply, just so we're noting on this, to 1. So if I had a 1 by 1, all right, this is 1 times 1, which is 1 squared, and it equals to 1. So essentially, we get these series of numbers which are perfect squares, starting with 1, then it goes to 4, then it goes to 9, then it goes to 16, and it continues. So the next one will be 5 squared, then 6 squared, so on and so forth. And we refer to these values as perfect squares. Like I said, they're a good set of numbers to get to know and become familiar with. Now, an extension to that is thinking about, well, if this is what a square is, what is a cube number or a perfect cube? Okay, well, essentially a perfect cube, we start thinking about our problems in 3 dimensions. So previously we were looking at 2 dimensions. This is where my drawing is really going to be tested. But if we looked at a 1 by 1 by 1 cube, like this has side length 1, side depth, or the depth of 1. We end up with one little cube to be able to build this, okay? So the total here is 1, and this is essentially saying it's 1 times 1 times 1, which is 1 cubed. Now we can extend this to build a cube out of little cubes that are 2 by 2. Like I said, this is really going to test so that's 2, my drawing skills here. That's 2. Hang on, that's dodgy. So that's my sort of big cube that I'm building. I hope you can see it. We're kind of building the big cube this way, and then it's divided by 2 little squares this way. So it's 2 by 2 by 2. All right, now you're going to have to use your imagination a bit here to work out how many blocks would that take to build it. All right, you can see that I've got 4 at the front here and then sort of 4 at the back as well. So we've got a total of 8 little cubes to build this bigger cube. All right, if you've got little cubes around and you want to play with this just to get a better picture of that, by all means. I just don't have that available. But essentially we can get that by going 2 times 2 times 2, which is 2 cubes. So 2 cubed is equal to 8. And we can continue extending this. So, you know, I can draw another cube. This is probably the easier way to do it, actually. And break this up into 3s. So that's a 3 by 3. Like so. This was actually a lot better than my previous effort. Oh, no, spoke too soon. So it's a 3 by 3 by 3. Now, you got to picture this. We're on the front face here, we have, what's that, 9? All right, and we've got 3 rows of 9. So that's going to be 27 squares in total to build this 3 by 3 by 3 cube up. Now, we can get that value by doing 3 times 3 times 3, which is the 3 cubed, or 27 in total. So our cubic numbers are essentially just applying the same logic but to a 3-dimensional sort of problem, and we get a list of numbers that are perfect cubes. All right, so 1, 8, 27, and then that would continue. Okay, so those there are what we referred to as square numbers and cubic numbers. Now, powers of 3 are our cubics, powers of 2 are our squared numbers.